first really preaches is gracious professionalism and cooperation, and that is giving this knowledge to others that may not have access to this knowledge when you're able to do so. So we will begin with a roadmap of what the course looks like. Today we're going to be going over mechanical design principles. That includes different types of calculations that are relevant, gears and pulleys, mechanical mechanisms, and component specifications. Next week we will go through OnShape parts and basic controls, talking about sketches, design intent, very important, and specifically the whole wizard feature, which I think is very underutilized by most teams. And following that, we will go through OnShape assemblies, proper mating, how to use the fasteners built into OnShape to make things quick and efficient, importing purchase parts and bills of materials so you can have a full list of what is on your robot when you are done designing it. After that, we'll do design principles, talking about designing around ease of assembly, designing around strong parts, designing around lightweight parts so that your robot can go faster. Talking about some material selection. We'll go through electrical principles a couple weeks from now, talking about Ohm's law, voltage, amperage, resistance, power, binary and digital signals, which will be very important if you want your robot to use any kind of sensors, analog signals, same boat, and then some miscellaneous topics such as 3D printing, considerations. Maybe we'll look at how to use some slicers, talk about some general things like game strategy, and talk about the importance of being able to sketch your concepts to convey the ideas that you have. You may not know how to CAD, but you can still convey useful and excellent ideas. To start us off, we'll go through some important equations and terms. The first one is given to us by Mr. Newton himself. F equals ma, force equals mass times acceleration. A lot of times force will show up in newtons or pound force as opposed to pound mass, which, funny enough, is typically a 1-to-1 ratio. Torque is an important one, something you'll see a lot dealing with the electric motors. Torque is a force times a distance, typically read in Newton meters. I saw on GoBuilda's website they had it in Newton centimeters, or inch pounds or foot pounds, depending on if you're using empirical measuring units or metric measuring units. Rotations per minute, RPM, you'll see that a lot. That's very useful for determining speeds, which typically the faster your robot, the better your scoring potential. However, you don't want to be too fast, otherwise you can generate some problems. And center of mass. Center of mass is a funny one. Center of mass is useful, such as this past year, we had to hang our robots. By hanging the robot, you needed to be all the way off the ground. And if your center of mass was not in the right spot, your robot would swing and potentially touch the ground. So how do you calculate your center of mass? Well, you could calculate it by hand. You could add up all the weights in the center of those masses and add them all up and find your center of mass, but that's kind of difficult to do. You could throw all your components into CAD. By throwing your components into CAD and giving them the proper weights, especially important for purchase parts, the CAD can actually tell you exactly where your center of mass is if your data is accurate. If it's not accurate, it will be inaccurate on the center of mass. Or you can calculate it empirically through experimentation. How would you experimentally calculate your center of mass? Any ideas here from the audience? You could try to hang it. Actually, if you hang it in 2 points, that is exactly how you can find your center of mass. If you add a bar and you hang your robot from one side, this line here will give you one position. And if you hang your robot from the other side, whatever line is generated there, which typically would be in gravity, where these two lines meet, is actually where your center of mass is. So you could hang it by 2 points and find exactly where your center of mass is. You might have to do 3 points if you are not hanging by 2 pieces. If you're hanging by 1 and you're finding it goes side to side, you could do the same thing in 2 dimensions to find where your center of mass is. We will start with purchase part specifications. Why do we start with purchase part specifications?
Purchasing a part is easier than making it.
It is true that purchasing a part is easier than making it. It's typically true that it's more cost effective than making it. But you typically don't want to modify purchase parts. So rather than designing something and trying to find the perfect thing that fits in there, you start with the thing that you know fits and design around it. It's a lot easier to change your 3D printed parts than it is to try and change a go build a motor. There's a couple places that you can find purchase parts. Go Build is a pretty big one. You can get parts from McMaster Car. On the screen here you can see what the McMaster Car site looks like, or typically you purchase parts from Andy Mark, such as The Field. There are a couple of other places, but from what I've seen, those are the most common ones used in FTC. If we look at specifically a Go Build a torque servo, I went to their website, and this is what it gives me. It gives me exact dimensions for all of the bolt holes. It tells me what kind of thread goes inside the sprocket for the output. It tells me where my mounting holes should be and what size my mounting holes should be. And it gives me one other very important piece of information. Does anyone want to take a guess as to what that most important piece of information is?
The cost.
That is very important, but that's not the most important. The most important is the part number. It gives me a part number. See if we can laser point it. Perfect. Right here. That is the part number. With that part number, I know exactly what part I'm talking about. I don't have to worry about whether I'm talking about a 5-turn torque servo or a standard torque servo, because I know exactly what the part number is. I can type in that part number on Go Builda's website, and it will bring me straight to this. Go Builda gives us a lot of information on their servos. We also get a lot of information on all of their other components, but this is the range of information that is just on their servo page. And this is a lot to take in at once, but there's a couple of really important things to take away. One is the weight. It gives you the exact weight. So when you import it into CAD, you don't have to worry about assigning it a material property. You can override the material property and give it the exact weight that it says, which is going to be accurate because this is what the manufacturer says about it. So when you're doing your center of mass calculations, if you override it and input this weight here, then you don't have to worry, is it the actual correct weight? Another important thing is the 25-tooth spline. That tells me what parts are going to mate with it perfectly. If I get another Go Build a part that says it works with a 25-tooth spline, I know it will mesh perfectly. The other important information here is actually the stall torque. You'll see they have a couple of different ones here, and it's actually a range. They just give you 3 points of information. And they give you the torque values in ounce inches instead of pound inches and kilogram centimeters. This is kilogram mass, which for the current purposes is effectively the same as Newton meters. It's not really true, but it's close enough. You will need to know when you set up and connect to your battery which of these voltages you're looking at. So when you design it, typically it's best to design around the lowest one, 4.8. If you are plugged into your control hub, I believe it gives you around 5, depending on what other draws are happening at that time. So if you use this top torque here for the stall torque, you'll be safe. You know you'll be able to at least overcome that. So if we wanted to design a gripper, we'll go ahead and erase some of this. To pick a pixel, just a simple claw. And we wanted to attach it directly to a servo. This is our little servo here. It's a little narrow, but that's okay. And we wanted to attach a claw to this so that we can pick that servo. How do I know if that servo is going to be strong enough? The answer is when I put a pixel in here, and we're using a pixel as an example because that was last year's game element. When I squeeze here, it will generate a force at this distance. And a torque is force times distance. So if we say this is I don't know what that would be, maybe 50 millimeters. And we know our max torque given here is 240 kilograms, 240 ounce inches. It'll be 17.2 kilograms centimeters. That will equal F times 50 millimeters. 50 millimeters is how many centimeters? 5 centimeters. Divide by 10. And then you bring this to the other side. The centimeters will cancel out, and it will give you a force in kilogram mass. I don't have a calculator on me. Can someone do that calculation for me? Be very kind. I guess that would technically be kilogram force, not kilogram mass. Excuse me. 3.44 kilogram force is what I'm hearing from the audience. Is that accurate?
Yeah.
Okay. So I know that if I'm squeezing more than this, I'm going to stall my servo. And that was quick and easy for me to calculate. So I can control the position of this servo. And if I move it way beyond what the closed position is, while that may give me a good grasp, it could also over torque my servo and either damage the servo or stall out my control hub, causing my whole control hub to disconnect. I don't know if that sounds familiar to any teams out there. But knowing where you need to be, it is important not to go too far beyond that, or you can cause problems, because even though it may not break, it may cause other problems. There's two types of motion we'll talk about. The primary is rotary motion, and the second one will be linear motion. Typically for FTC, linear motion is derived from rotary motion, but we'll get there. Rotary motion is generated in FTC by servos and motors, DC motors specifically. That is what is legal. I don't think there's any other way of generating power in FTC that I'm aware of. Even linear actuators that are purchased are driven by servos. So if we're looking at something like a drivetrain, how do you know what motor you should use for your drivetrain? Well, if I go to GoBuilder's website and I go into their DC motors, they give me a big list of part numbers here, their speeds and their torques. So what do you need to know about your bot? You need to know the weight of your bot. That's easy enough to figure out if you just put it on a scale. You need to know the diameter of the wheels. If you go to the purchase part specifications, they'll tell you that. In the case of the GoBuilder wheels, the Mecanum wheels, they're 96 millimeter diameter. And you need to know if you've put any pulleys or gears in place. If you've geared up or increased your pulley diameter, have any kind of ratio there, it will affect your calculations. So if we assume that it's 1-to-1, maybe you're direct driving, maybe you've put a pulley that's the same size on the motor as you did on the wheel. We're using the Mecanum wheels of 96 millimeter diameter. The bot weighs, let's say, 10 kilograms, and we're using 4 wheels, and more specifically 4 motors, each one driven. And we have a central center of mass. We can determine what the torque requirement is. Where does 4.8 centimeters come from? Any guesses?
Half of your wheel diameter.
That is half the wheel diameter. Why would it be half the wheel diameter? Because if there is a wheel with an axle and it is pushing on the ground, this is where the power is coming from. So this distance is 1/2 diameter, which happens to be your radius. And this is where your applied force is. So that is exactly right. When you're looking at force times diameter for torque, this is the, force times distance, this is the distance we're looking at. We have 10 kilograms divided by 4 wheels. Why would we divide it by 4 wheels? You have 4 motors driving it. So that weight is spread out over 4 wheels. And if we do that calculation, it comes out to 12 centimeter kilograms. Based on that, which of these motors should we choose? Which RPM value?
435.
That's exactly right. So 435 is chosen because you need at least 12 centimeter kilogram. If you go over, you just have extra strength there. In fact, it's typically better to go over. If we somehow manage to drop our bot's weight and we get it under 6.5 kilograms, that drops it to 7.8 centimeter kilograms. And that would put us under the next size down, and we could put on motors that are almost 3 times faster, meaning your bot would be almost 3 times faster so long as you stay under 6.5 kilograms. Gears. Gears is something that's used a lot. These are all of the gears, or some of the gears, that GoBuilda has just on their website. And this isn't even all-inclusive of all the types of gears that exist. This is just the ones that are typically used in FTC. When you calculate anything related to gears, you have to look at the pitch diameter. Does anyone know what the pitch diameter is?
The internal diameter not from the top of the tooth, right?
It's from where the teeth mesh, right?
It is the engagement point of where the teeth mesh when you put 2 of them together. It's not quite halfway, but the manufacturers of the gears will do all of that math for you and tell you exactly what the pitch diameter is. In this case, again, I went to GoBuilda's website, and they told me exactly what the pitch diameter is for this gear. When you look at gear ratios, you hear lots of people say that our gear ratio is 10 to 1, 50 to 1. All that is a straight multiplier across the board of any of the values you get with some variation in between. The important thing to design around when you have multiple gears is that they all have the same pressure angle. What is the pressure angle? I'd be surprised if anyone knew this.
Well, it's the angle that the teeth are at, and basically the higher the angle, the more pointy the teeth are, right?
That is
Or is that exactly
correct
opposite?
enough. I don't actually know off the top of my head what the pressure angle is, which is why I would be surprised if anyone else did. What I do know is it has to do with the angle of the teeth. And if I use 2 different pressure angle type teeth, they will not mesh together very well, if at all. So you want to make sure that your pressure angle matches across whatever gears you're using in your gear train. When you look at a gear train, what is a gear train? A gear train is a series of connected motors. Gear trains can be connected either by tooth engagement, or 2 gears can share the same shaft or be coupled together in some way and will turn at the same time. That's what's called a compound gear train, when you have lots of teeth stacked up and you end up with multiple gear ratios. So when you look at gear ratios, everything is exactly that, is a ratio. Some comparison of 2 values to a comparison of the other 2 values. There's a couple of key terms there: diameter, number of teeth shown by N, angular velocity, or speed, as we normally call it, and torque. So your gear ratio is your diameter out over your diameter in. Or it's your number of teeth out over your number of teeth in, or torque out over teeth in. When you get to the speed, what happens when you start getting bigger? If we have a large gear and a smaller gear, let's draw that much smaller so it's exaggerated. And we will say that even though these may not be the case, this is 2 times the radius, and this is 1 time. If I apply a torque here, that torque has this distance to go, which is 2r. If I apply a torque here, it's 1r. So there is a force being applied here, And we know by our equation, I'll write it bigger so the camera can pick it up. The farther our distance goes, if this becomes twice, the torque is twice as much with the same amount of force. But typically, as you see here, the torques are a ratio. So torques will be shared across, and I can only put so much force here. So if I want the same amount of force, and I give it twice as much distance, then I'll have twice as much torque given here. Speed, on the other hand, because this takes one full rotation, speed is typically in RPMs, is what we know it, half of this will have gone around by the time that the same number of teeth here go around. So this will be moving twice as fast with half the torque because the distance is halved. So speed and torque have an inverse relationship. Does that make sense? Are there any questions related to that? You don't need all of these values to be able to calculate your ratio. You really only need a couple of them. So if, when in doubt, you could always just count the number of teeth. I have a question in the back.
A good way to remember it is driving gear over driven. So
That is correct. Driving gear over driven. So in this case of what the example shows here, gears aren't typically drawn with all of their teeth. It takes a lot of time. We typically draw them as circles. So if I have one gear that has 16 teeth and one gear that has 8 teeth, my gear ratio ends up being 2 to 1 or 2. If it was the opposite and I was driving this one first, and this is the driven gear, the larger one, then it would be the inverse. I'd have a 1/2 gear ratio. When I'm designing putting gears into my robot, how do I know how far apart I need to space the gears? The pitch diameter.
Pitch diameter? You want me to say it again?
The pitch diameter. The pitch diameter tells us this distance from the center. You can get the distance from the center to the pitch diameter by dividing the diameter by 2, the pitch radius. And you want the pitch radius to be directly on top of each other when you have 2 gears next to each other. So you'll take the pitch radius of one plus the pitch radius of the other and add those together, and that should be your center to center distance between your 2 gears. What happens if I stack a smaller gear on the same shaft as a larger gear? What happens to the torque, let's say? So instead of being offset here, we have a large gear and a small gear, and they share an axle. They're moving in unison. And if this has a torque of 5 Newton meters, how much is this one going to have as a torque? Also 5 Newton meters. It's the same because all of this is transferred through that shaft into this one. So if you are looking to do multiple steps, say one ratio isn't enough, you can put another small gear here and mesh it with another big gear. And you've driven this, doubled the torque, and then doubled it again, assuming that this and this are the same size and these two are the same size. So this is what we call a compound gear train. So if this has a ratio of 2, and then these two have a ratio of 2, you multiply those together and you get 4 times what your original was. This takes up a lot less space than doing progressively larger gears. Any questions on gears? For pulleys, it's pretty much the exact same thing. What's the difference between a pulley and a gear?
Pulleys use belts to mesh instead of using the teeth of the gears.
That is correct. Pulleys are almost always, if not always, connected by belts. You can stack them together. You can make a compound pulley system by putting them on the same axle. Typically, they are not translating force through an axle. It's not what pulleys are best for. If you need to do that, typically your forces are high enough to justify gears. But you can put them on the same shaft, have them idling, put another one on the other side, and because your belt can have a little bit of leeway to it, especially if you're not using a timing belt, say you're using a round belt, you can actually end up creating what's called a pulley block, which is a series of pulleys that has an input force and an output force that goes through a series of changes in a small area. The calculations are the same, but what is not the same is there's no end, there's no teeth on a pulley. So you can't do any kind of tooth ratio, but you can still do all of the other one. Torque, you can do speed, and you can do the gear ratio. How do you know how far apart to put two pulleys? That is a good guess. Is there a question from online?
There's a question from chat.
Okay.
Are tank treads or tanks pulleys?
I would consider tank treads pulleys for the sake of calculations. That is correct. I have an answer, but we need the mic over here. Question again is, how do you know how far apart to space your two pulleys? Where do you put your axles?
An approximate or a good approximation is usually like the half the circumference of the first pulley plus half the circumference of the other pulley plus 2 times the distance between the pulleys. It's a little bit more complicated, but I don't know what the actual equation is to calculate it out, and that calculation will get you close enough, especially for FTC.
We have two pulleys. They're the same size. What the answer was is you take this half of the circumference and this half of the circumference, and then the distance here to here, times 2, because you have 2 of those. And that would indeed add up to give you exactly what that gives you your pulley, your belt size, but that's belt size knowing the distance already. But the question is, what is the distance? So you can start with a belt, do this calculation, you know your pulley diameter, and you leave this as your variable, and it would give you that exact distance. So we're going to write that out. We will say our radius is 1 centimeter. And this one is also going to be a radius of 1 centimeter. And let's get a belt length of, let's say, 4 centimeters. I'm going to try and write that bigger. If you go to GoBuilder's website, they sell round belts, and they give you the total length of it. So this is a value you can get straight from the manufacturer specifications. So we're adding 1/2. Got to write bigger again. Apologies. Hard habit to break. Circumference 1 plus 1/2 circumference 2 plus the distance between them times 2. It's been a while since I've written on a whiteboard. And we will call that distance here. This is going to be our D. So you can calculate this using your 1 times radius. What does that give us for a total circumference? If your radius is 1 centimeter, how many centimeters is your full circumference? It'd be 2 pi. That is correct. And then you add that to another one, which would also be 2 pi, and then divide it by 1/2. So if we did 1/2 2 pi plus 1/2 2 pi, all of that just equals 2 pi. And then we still have to add in our plus 2d. pi is equal to 3.14. You don't typically need more decimals than that, but you can add them if it makes you feel good. And if you plug this into your equation for d, what does it give you? Someone with a calculator. And this would all equal 4 centimeters because that's the length of the belt. So 14.28. So your D equals 14.28 centimeters. Does that make sense? I don't know that everyone's getting that. Does that make sense? I saw some eyes in the crowd that did not see. Because I'm jumping all over the place?
A little bit.
Okay.
So I
We can rewrite this so it's a
I
little easier to
understand
see.
the calculation of the circumferences.
Sure.
But you're using 2D to equal D.
2D from this, so this would end up being 2 pi here. And it equals 4 centimeters because we bought a belt that is 4 centimeters. Does that make sense?
Yes.
So when you solve this equation for D, that's how you get D equals 14.28 centimeters. Well, I'm trusting your calculations, so double check it.
4 centimeters minus, wait a second. No, because
It's a negative number.
Because you have 6.28.
So how could that be? What would that tell us? The belt's too small. You got to go with a bigger belt. 4 centimeters is not enough. You can do a quick check on that because 2 pi is what you need right here if those pulleys were right on top of each other with 0 distance here. With having this 1/2 of 2 pi just equal pi, this is already 3.14. You add another 3.14, you're already at 6. This belt is way too small for pulleys of this radius. So if instead, let's go with a 14 centimeter belt. And this equals 14 over here. What does that give us? And let's try and calculate it correctly this time.
3.86,
Yeah, 3.858 is what I got.
3.85 centimeters. And that's realistic.
Too many significant digits.
So if you space these 3.85 centimeters apart and used a belt that was 14 centimeters instead of 4, you could make it work. You could also try and figure out what it is first for the distance that you want, and then find a belt that fits. As the answer was before, this is an approximation equation. This works exactly right if they're the same size. Very infrequently do we have the same size. So you could approximate it, and as long as you're using some kind of tensioner system that squeezes these belts together to get rid of that slack, you'll probably be okay. Otherwise, you could use trig to figure it out. We won't go through that example, but I will show you how you would set up that problem. So if I have a large pulley and a small pulley, and I wanted to try and figure out the distance here, it would again be one of the circumferences. It would be the other circumference, or half of it, I should say. And then this is a triangle where this distance is the radius of this pulley minus the radius of this pulley. So if this has R1 and this is R2, then R3 equals R1 minus R2. You figure out the hypotenuse of that using a variable maybe for the distance, knowing the belt, or finding the belt knowing the distance. You can only solve for one, and then you double that for the other side. Here's an example that I will let some people solve in their own time if anyone wants actual practice. This is a simple gear train where you have 4 gears of varying teeth size, and your job here is given a speed and a torque, find the output on the other end of the gear train for speed and torque, and then knowing the diameter of the first one, find the diameters of the other ones. We're not going to go through this now. If you want practice, you are welcome to do this in your own time. I believe we will release the PowerPoint. We can release the PowerPoint, or you can just watch the YouTube video, and perhaps we can bookmark it. Any questions on rotary motion at all? Rotary motion is pretty straightforward. Typically, it's motors or gears, motors or servos, and gears or pulleys. When you get into linear motion, in FTC specifically, you are using a servo or a DC motor to create the linear motion. You can either buy a kit that already does this for you, or you can design your own linear actuation system. Other types of linear motion that are not necessarily created by servos or motors are springs. Springs can generate linear motion if they start compressed and you release them. And you can generate complex mechanisms that do a very specific path of motion if you need some kind of specific path of motion. Anytime you have linear motion, you should be using bearings. Generally, bearings are used to either support the load that you are carrying so that your motor doesn't have to support that whole load, or you can use rotary bearings at key points such as your axles to prevent wear. If you have a part that's just riding over and over again on another shaft, eventually one of them is going to wear out. So you use bearings to reduce the amount of friction between them as well as make them all last longer. I don't think we've ever replaced a bearing in our robot, but I do know other teams that have, especially in swerve drive cases where those bearings are under a lot of stress. A pillow block bearing, such as you see here, can often be used to support the weight that is mounted to a servo or motor so that your servo output shaft or your motor output shaft is not carrying all of that weight, because that can damage your motor. Whereas if you take all those gravity forces and put them on a bearing instead, it prevents stress on your motor. And typically motors have a max rating, but I don't think GoBuilder rates theirs for cantilevered load on their output shaft. Slides are the first most obvious type of linear motion generated. Viper slide kits can be purchased from GoBuilder. Here's a couple of examples here. And they produce a lot of linear travel with a pretty good torque to speed ratio. But why would you want to avoid using a slide? It can be heavy and take up a lot of space. Take up a lot of space is what I was going for specifically, but you are right, they can be very heavy. They are great if you need to do long distances, but if you only need to move 50 millimeters, they may not be the best choice, because that's a lot of space taken up off the purchased kits for a very short distance of travel. So they may not be what you always want to use. Lead screws are generally the best type of linear motion for transferring torque, but that comes at a cost of speed. Lead screws can move fast, but they typically don't in FTC settings compared to some of the other options such as slides. Lead screws can be back-drivable or non-back-drivable. If you are purchasing the GoBuilder lead screw, I believe it is non-back-drivable. There's an equation you can find online that tells you whether it's back-drivable or not. But any guesses what back-drivable might mean without reading the screen?
Doing the same thing in the opposite direction from the screw?
Not exactly. That is the motor turning in the opposite direction.
It can't be forced from the output to move.
That
it
is
can only
correct.
be moved from the input.
Meaning only the motor can drive it forward or backward. You can't push on the shaft and have it drive forward and backward. If I unpower the motor and I push on the output shaft and it's not back drivable, then it won't move. It'll hold its own force. If it is back drivable, it will move. If I do the same with slides, I power the motor down, almost always they will just collapse on themselves. So one case that you might want a non-back drivable lead screw. Any ideas?
You want something to hold its position under no power?
That is correct, but what is a specific example of wanting something?
Mechanism.
A hanging mechanism. That's exactly right. So many robots in the last year used a lead screw to raise up their claw. They'd pull it down, and then you could power off your robot. You don't have to sit there and provide power to that motor, draining your battery, potentially overpowering your control hub. And if the control hub gets overpowered, then you turn off and you've lost your hang. Whereas with a lead screw, you might be able to just lift yourself, cut power, and you're just hanging there. You have no problems just sitting there hanging there all day. That's exactly right. It's very much like a winch. When we look at springs, there's a new calculation that you need to know. It's fairly simple. It's called Hooke's law. Hooke's law is force times a spring constant. Force equals a spring constant times a distance. That spring constant is typically read as K. Why it is K, I could not tell you. You can research that in your own time. But F equals KD. So spring constants are given per spring. You don't always have access to the spring constant, but getting the spring constant will give you access to this full equation. So if you have a known force that you want to generate, you can find a spring that has the spring constant you want, and you know exactly how far you have to actuate it. Or perhaps you know how far you're actuating it, and you want to know what the force is that you're applying. Using your spring constant, you can generate that. Excuse me. If you don't have your spring constant, how could you get it? By knowing the force and the distance. So how might you know the force and the distance?
With the Newton meter? A force meter?
A force meter, also known as a scale. If you have a fish scale, for example, fairly inexpensive tool, you can pull a known distance and you can approximate your K value. The more accurate your tools of measuring your distance and your force, the more accurate your K value is. But if you absolutely need it and you don't know what it is, you could approximate your K value. There are different types of springs. The most common ones that you'll see in FTC are the extension or tension springs. They're called the same thing. If you looked up tension spring or extension spring, you'll find it. There's compression springs. Those are the ones that most people think of, that you squeeze it and it pushes back. And then there's torsion springs. They typically work in a rotary motion as opposed to along the axis motion. There are other springs. There are lots of other springs, but you're not typically going to find them in FTC. And you're not typically making your own springs either, which is something that could be done to give you a very specific force curve as it's moving. They're called variable springs. If you overextend or overcompress your springs, you can damage them. Some springs cannot handle being compressed to what's called their solid length. If you squeeze it all the way down and it's touching it ring for ring, that's called its solid length. Some springs cannot handle that. Most of the springs you'll buy in a hardware store can, but it's more obvious in extension springs, which have the little loops at the end. If you sit there and pull them, eventually you're going to pull it beyond where it's able to pull back. There is a question.
Is the K value potential energy?
K value in this case is not potential energy. It is a constant given by the spring, and the K value is typically in pounds per inch or newtons per millimeter, kilograms per millimeter, kilogram force, but it is not quite the same as potential energy that you would see in physics. This screen grab is from McMaster. In this case, they're showing a 1/4 inch long spring This is an extension spring specifically, and it is giving you the spring rate in pounds per inch right here for a variety of springs, and it gives you a max force at this length. So you achieve your absolute max force, which is given right here, at this length. Typically, if you exceed this length, you're going to start damaging your spring. But if I know that I need a specific K factor, then, or I need a specific force for a certain distance, I can find a K factor, I can go and do that calculation, and then go on to somewhere like McMaster and sort by the K value and find exactly what I want. So there's another practice problem that you can do in your own time. If you have a spring constant that gives you, find the spring constant that will give you at least 11 pounds of force over a distance of 0.4 inches. So you need to find what is that spring constant, that minimum, and then your next task is to go to McMasterCar.com and find a spring that meets this requirement for both an extension and a compression spring. And I think we'll post I actually pulled some that are correct answers. There's lots of correct answers because this is bottomed out. There's only a minimum force, and you can go well beyond that, but I do have some answers for that if someone wants to look into it. We have 4-bar mechanisms. Now we're starting to get into the complicated stuff. There are lots of different types of 4-bar mechanisms. What is a 4-bar mechanism? Any guesses from the audience? That is correct. The answer is a mechanism with 4 bars. But the 4 bars aren't always obvious. This is a 4-bar mechanism, but I only count 3. So where is my 4th? Technically, it is the floor. If I had a beam right here that was anchored, that would be my 4th. This one is the same thing, but this one has a moving piece here, and technically that means my 4th bar is of variable length. You have a couple of different types of motion that you can generate fairly simply from 4-bar mechanisms. If you have a moving point shown, moving pivot up here and here, and I pull on this, and it rotates about that point, it pushes the other direction. Perhaps you want a push-pull linkage, so it does exactly what I'm doing. So you can do a multi-bar mechanism that allows you to do that. You can have parallel motion linkages. This is a pretty cool one that I think we'll end up bringing back up in one of our CAD classes. But if you have the exact same length on these two members, that bar will always stay parallel to that bar. And then you can actually do what's called a bell crank. This is moving it about a different point, and it takes one direction of motion and turns it into another direction of motion. I posted a website here. This is where I pulled all of these images from, and they go into detail about all these different types of mechanisms and when they might be useful and how you generate them. So the best way that I have found to determine what your linkage needs to be is you can either use CAD, which we will go into in a separate class, or you can prototype in cardboard. If you cut some lengths of cardboard out and you put some little holes in it at a known distance from each other, and you just put a little pin in it, you can play with 4-bar mechanisms to try and generate whatever path you want. That's the simplest and most effective way to practice with it. They will need to be anchored in some way. You have to have a reference point from which you are starting to move. And if I change the pivot point, such as this one right here, if I move this down a little bit, that's going to change the motion of this whole mechanism to where it's effectively an oscillating like this. If I took this beam and I just shortened it to about half its length, that's how you generate this exact same picture here. So in this case, they're rotating fully about A, and C is just moving back and forth. And depending on the length of this A to B beam, it will change what that oscillation is all the way until it's moving in a straight line. The farther down it gets, the more of an angle it gets as it rotates. There is such a thing as a virtual 4-bar mechanism. Any ideas what what the virtual 4-bar mechanism might entail from someone who doesn't know the answer? Okay, we'll allow people who know the answer to answer the question too.
It's a 4-bar where one or two of the bars comes from something like a belt or a chain.
That is correct. So it's a complicated thing to try and wrap your head around. So videos are generally the best to show it. But if I was to take a bar, a single bar here, let's see which one might be the best case. This one. If I was to take this bar and I was to wrap a pulley and tie that pulley to a second pulley that's attached to this bar BC, as I rotate, the belt generates a rotation in the pulley that's at this anchor point. And what that does is it rotates B and C without needing this additional bar, so it's taking up the place of that bar. So we're moving A to B back and forth, and it's moving B to C in a known path without requiring this additional linkage. That's really good for things that have to leave your bot. You don't have that extra anchor point out there. So you can do virtual 4 bars to generate motion that exceeds where your bot's footprint is and then comes back into it. Again, the best thing you can do here is play with mechanisms. Generate it in CAD with some simple sketches, which will show you how in the future, or generate it in real life with some simple cardboard pieces, because the possibilities are pretty much limitless, and you can generate any path you want. There is a way of starting with your path and generating the bars from that, but it gets much more complicated. The last mechanism we're going to talk about today are slots, the value of putting slots in your components. This, on its own, is not really anything that's considered a mechanism, but I've put it in here because it allows you to control the range of motion from what you're generating. So some examples of that are the Geneva wheel. These are technically little slots here. So as that pin moves into the slot, it forces it to rotate around, and you're turning rotary motion into what's called an index motion here. This has a very similar pin. So as this rotates, that pin's going to move down in this slot and pull it back at the same time. And then it's going to continue to rotate. It's going to start moving up while it still pulls back. And then it's going to push it forward in the top half of the rotation. So you get linear motion out of rotary motion using slots in a simple mechanism. So this takes this distance here and makes it linear motion while eliminating any kind of up and down movement. The top picture here is a similar concept where you have a pin on a mechanism, and it is on a pulley, and it is rotating, and it's causing this to have some kind of movement, but because it is pinned instead of constrained on the outside, it is actually going up and down instead of in and out. Open source had a pretty unique claw mechanism for this past year. Open source's team 213 out of Houston, Texas. They had a dual stage pixel picking mechanism. They would put it on the inside hole of the 2 pixels when they were stacked, and using one servo plus a couple of rubber bands, they were actually able to independently control the 2 pixels. And they were able to do this because their engagement happened at different points in the claw opening and the rotation of the motor due to slots. Are there any questions on slots? Slots is another thing that is best to determine through experimentation.
In case you're wondering, the image in the bottom right is called a Scotch yoke.
A Scotch yoke? I learn something new every day. That's all I have for today. Are there any questions in general? We are getting none from here. If you do have any questions, you are free to leave them as a comment on the YouTube page, and we'll see what we can do to help answer those. Otherwise, we will see you all next week for the first of the CAD classes. I got a finger up from the tech team in the back. Is there another question happening in the chat?
Just give me a couple seconds.
Okay. Are there any other questions in general from the room? Seems like we are good to go.